So the idea then that this dimensional resonator basically is the idea that when things either change their order of their motion or change the direction of their motion, that either way it involves getting back to that. It's in terms of the linear elements of that over time, and as well the linear elements of forward and back of that over time, so that you have both kind of the meters per second and seconds per meter. Is it meters per second or seconds per meter? Yeah, it's meters per second or seconds per meter, and it's meters per second and seconds per meter. So now I just figured that out just now. The idea that the units kind of come together, because that makes a dimensionless thing, a dimensionless term. And otherwise, that the parameterization, which results that according to this force, meters per second changes like so. Velocity changed, v dt, acceleration changes like so. Or deceleration makes it like so. This force of static friction, or dynamic friction as it were, or as the function of it as a function of time, applied means that this block will slide to a stop like so. Seconds per meter. These are, so this is now the new idea involved with the dimensional resonator, is that there's sort of a dimensional alternator. And the idea is that then one of them is associated with the direction, and the other one and changes in direction, and the other one's associated with the order of the quantity of velocity, or here inertia, if it's to be an inertial system. Now, I'm not really familiar with this kind of development yet in the mathematics. Now, I have a mathematics degree, and when I sat this mathematics degree, it was to get, a good amount of study. And I studied foundations a lot. Really, my study is foundations. So that's like descriptive set theory, axiomatic set theory, what gets involved with all the paradoxes, resolving all the paradoxes of mathematical logic. And they have truth, a truth value system. So foundations is just theory at all, a theory. It involves mathematics and then science and physics. So here in the physics, then the idea about these laws of classical motion are to separate the constituent components as what involved in how they have a formal description. And then here with regards to the parameterization of a formulaic approach of a function that defines a value given a time, everything parameterized by time, a single continuous quantity shared by all, universal clock hypothesis, basically, is that then the classical is always linear, meaning it's always, anything is just going straight in its direction. And then as with regards to that being a composition of vectors affecting it from moment to moment, the kinematics of the geodesy of a body, each of its moments as masses, those all orbiting one another in terms of one straight line, has the results that it's one way to think about it. The forces as about a body representing also the forces within a body, so that again it's kind of like Feynman closed the last discussion, was that force is the classical limit that results a description of a value, that results a vector, that results an addition of vectors to result a known quantity in the model that happens to match what Galileo says. And as with regards to that, it matches what Lorentz says, is with regards to kind of some highly contrived relativistic systems where The boost is two vectors adding together largely at their ends. Now, that's a little underdefined, but it's just to relay that it applies both to the very, very small, the very, very large, everything in between. It's all one law. Nobody's quite sure what it is. The idea then of breaking down the components to make like a path integral and a walk integral kind of a thing, in terms of having the rotational components and the components otherwise of acceleration making for a kind of unified and combined model of an object in its motion that should look exactly the same as an inertial system. And of course, all its classical quantities are going to be classical in limit because they are. They just, it doesn't explain how to get from point to point very easily. It's just kind of like, start something rotating and then just follow it around. Well, how do you follow it around? It's like, well, it follows itself around without any work at all or something like that, To relate and relay that it comes around. Vis-a-vis, otherwise, how the classical model is very much like a matchsticks all built together. And there's an idea that it's still, in a sense, that the transformations and difference between those have a way to help relate them in effect. So, yeah, so far this talk is pretty much about that. Meters per second and seconds per meter together make a dimensionless quantity. Then with regards to what else goes in the derivations as quantity as an operator for an algebra. So basically that usually when you put quantities together according to algebra, it's their product, their terms, or they're on either side of the solidus or equals bar. Or their inverses, the solidus being like the divisor bar. Or that it reflects some kind of a quantity that then carries in the derivation. What it means then when something's going straight and turns and is again going straight, that there's nothing left at all behind it. It is as if it always was, free in its own rotational setting, while at the same time in carriage in its linear setting. So that the units are always linear and forward vis-a-vis the operator that gets applied to the left or right, in a sense, keeping things simple on a line or on a plane. Then with regards to that being the most usual notion of motion and the most readily available setting that's just above classic animal motion, and highly energetic in a sense. So that's the idea today so far, is that in terms of analyzing classical motion and figuring out after the under definition of moment or motion and rest and equal and opposite reactions in forces, mass times acceleration, the definitions of torque, well, that kind of follows, but definitions of momentum, the definitions of inertia, the orders of inertia and the orders of momentum variously, when it's mass and velocity together, those as quantities with regards to the one and the other, the terms about dv dt and dmv dt, and about 1/2 mv squared, which kind of looks just like that, dv dt. And that as g and that squared and its orders, keeping it that way. In the dimensional analysis, it speaks a lot to what's going on with the under definition of classical motion, and linear and rotational are for the kinetic and kinematic, and why that helps affect to relay what goes on with tribology, what goes on with spinning wheels, vertically and horizontally, helping explain these other terms and effects. Essentially, the result for this sum of history is sum of potentials theory. It is a true centrifugal. And then the objects they rotate in their frames, and there is mass energy equivalence in the energy rotating in the frames. Not necessarily so as turning, but as a part, because that's just a moment that exists and disappears. It's a flex. Whereas something that's rotation actually spins and gains a moment with regards to its standing behavior, the fact that it is as of it's oriented and it's upright in a sense, to help affect then what that means and why it's so that the angular momentum and this sort of thing, because it ends up being just kind of its own little system at rest, is well defined in the moments, but inertia there's no moments of inertia of the moment of inertia, because by the time you turn it around and add it up, it would need to have this dimensional analysis put in place for it to be a real thing, to bring inertia back into motion, linear motion. Well, that's something I'll be thinking about for a while now. That is the idea to associate the dimensionless quantities in terms of still particularly kind of the prime units, meaning the linear units in a space. This would be like meters in length and grams, of course, for mass. With regards to then something like the gram atom, or relating units of length and mass with regards to how far a given mass moves as length given an applied unit of force, which is otherwise kind of a fabricated quantity. Again, about the dimensional analysis, the real analysis involved in this walk integral, and about a natural units, and these kinds of things. Let's see what Feynman has to say about this. Well, what he has to say is, here's 3 lecture books. They're lecture volumes. They contain everything you need to know. It doesn't quite fully explain everything, but if you can't figure that out, at least it'll keep you busy for a while. So, it's all about quantum mechanics. It's got probability amplitudes. So, that's how these things add up in the model of particles and waves, when the real wave collapse isn't really modeled because it's kind of a supermodel and needs its own analysis. What comes out as observables is kind of a result of these probability amplitudes. If you wait long enough, one will show up. That's kind of how that works. And so there's Stern-Gerlach. I want to read some more about Stern-Gerlach. And last time we looked at forces, the classical limit, uniform motion, atoms at rest, stationary states, how states change with time in the Hamiltonian matrix, what are the base states of the world. Let's take a look at that for a second. The Hamiltonian matrix, section 8. The idea then, so we've got the scattering matrix just before this. How states change with time. Hydrogen, the particle. Does a proton have internal parts? What are the base states of the world? You can, for instance, project a spin in the z direction or in some other direction. There are many, many different representations which are analogs of the differential coordinate systems one can use to represent ordinary vectors. So yeah, in the linear space, everything adds up. And at any given moment in time, all going one direction and all along one route, it says so. And anything that's in a different coordinate setting, it's got a different origin, if any of these space frames is his own frame space in a sense, gets into why what Feynman writes is pretty profound sometimes. Next, what coefficients? Well, that depends on the physical circumstances. Different sets of coefficients correspond to different physical conditions. The important thing to know about is the space in which you are working. In other words, what the base states mean physically. So the first thing you have to know about in general is what the base states are like. Then you can understand how to describe a situation in terms of these base states. We would like to look ahead a little and speak a bit about the general quantum mechanical description of nature in terms of the current ideas of physics. So, of course, this was 40 or 50 years ago, but they're still quite current ideas in physics. We pick a set of base states, each corresponding to one value of the momentum. What if the electron doesn't have a definite momentum? That's all right. We're just saying what the base states are. If the electron hasn't got a definite momentum, it has some amplitude to have one momentum and another amplitude to have another momentum, and so on. And if it's not necessarily spinning up, it has some amplitude to be spinning up going at this momentum and some amplitude to be spinning down going at that momentum, and so on. So in the wave model, it's globular. It's globular, but it's lobular, and it's kind of lobular in all rotations at once. If the electron, and if it's not necessarily spinning up, the complete description of an electron, so far as we know, requires only that the base states be described by the momentum and the spin. You hear that there's a sort of isospin, and that momentum is what results as, well, according to potentials, what results, and that it is a potential. So electron physics, of course, is Feynman's great field. Resolving state vectors, amplitudes and vectors. We explain this in terms of a Stern-Gerlach apparatus, but we remind you that there is no need to have the apparatus. Equation 8.1 is a mathematical law. Chi phi cat equals sigma of all I brac chi I cat brac I phi cat. So that just has the i's in the middle. It's given the conditional probabilities of the amplitudes, it's the usual way that bracket notation or Dirac's or what it is that, and then it's so. But now I'm really curious about the Stern-Gerlach apparatus, because what it reflects is kind of the effects. It's getting into effects. Filtering atoms with a Stern-Gerlach apparatus. Spin 1. All right. Filtering atoms with the Stern-Gerlach apparatus. In this chapter, we really begin the quantum mechanics proper, in the sense that we're going to describe a quantum mechanical phenomenon in a completely quantum mechanical way. We will make no apologies, no attempt to find connections to classical mechanics. We want to talk about something new in a new language. The particular situation which we are going to describe is the behavior of the so-called quantization of the angular momentum for a particle spin 1. But we won't use words like angular momentum or other concepts of classical mechanics until later. We have chosen this particular example because it's relatively simple, although not the simplest possible example. It's sufficiently complicated that it can stand as a prototype which can be generalized for the description of all quantum mechanical phenomena. Now, in the path integral, we know that things largely add up largely according to the classical action. But here, Feynman's just kind of getting to explain that quantum particle, in terms of its attachments, its classical action, in terms of the quantities, which are to arise and get added back up and to reflect the same energies, that then this assignment of a number as an indicator is reflects the system. It is sufficiently complicated. Thus, although we are dealing with a particular example, all the laws which we mention are immediately generalizable, and we will give the generalizations so that you will see the general characteristics of a quantum mechanical description. We begin with the phenomenon of a splitting of a beam of atoms into 3 separate beams in a Stern-Gerlach experiment. You remember that if we have an inhomogeneous magnetic field made by a magnet with a point and pole tip, and we send a beam through the apparatus, the beam of particles may be split into a number of beams, the number depending on a particular kind of atom at its state. So I just imagine this looking as like a Van de Graaff generator or something like that, which kind of on the globe about the electrode make it so that the potential is so within it that it will just kind of, its potential is to have multiple arcs at once in the Van de Graaff generator of the globe, and but not just one, as if it was just like a wandering arc, but actually as if, however the potential was that it split it everywhere at once. That the Van de Graaff generator is also a good visual thing to see with regards to quantum mechanical behavior at work. Into a number of beams, the number depending on the particular kind of atom and its state. We're going to take the case of an atom which gives 3 beams. We're going to call that a particle of spin 1. You can do for yourself the case of 5 beams, 7 beams, 2 beams, etc. You just copy everything down, and where we have 3 terms, you will have 5 terms, 7 terms, and so on. Imagine an apparatus. It's a beam splitter in a sense. It's got an atomic beam and horizontal to it, or perpendicular to it is a magnetic field gradient, and so some of the particles get deflected either way because they have micropole moment magnetically. Thus, some of them are 0 and some of them go either way. Imagine an apparatus. A beam of particles in any kind is collimated by some slits and passes through a non-uniform field. Let's say that the beam moves in the y direction and the magnetic field and its gradient are both in the z direction. Then looking from the side, we'll see the beam split vertically into 3 beams. Now at the output end of the magnet, we would put small counters which count the rate of arrival of particles in any one of the 3 beams, or we can block off 2 of the beams and let third go on. Suppose we block off the lower 2 beams and let the topmost beam go on and enter a second Stern-Gerlach apparatus of the same kind, shown in figure 5.2. What happens? There are not 3 beams in the second apparatus, there's only the top beam. This is just saying when something's spinning or turning like that, and according to this apparatus, it's out the edge of the field, as it were, and it keeps turning the same way. The particle is a real wave. So it's just helping explain here that this is just this aspect of its spin is where it lives in the field, where it lives in the wave. And that's what, so Feynman says it just keeps, so if you have a circle of these in a circle, it will, you can rely on that the ray splits while keeping its diffraction in that sense. This is not what you would expect if you think of the second apparatus as simply an extension of the first. Those atoms which are being pushed upward continue to be pushed upward in the second magnet. So it's kind of like what was blocked off or not propagated gives its component to what does continue. The wave collapse is everywhere, but the Fresnel principle is that waves are always just emitting little waves. And so this is like the bigger wave that carries through the Stern-Gerlach apparatus. Well, then he has a whole half page now is in this next diagram. So you can get then that the first apparatus has produced a beam of purified atoms that get bent upward in a particular inhomogeneous field. The atoms as they enter the original Stern-Gerlach apparatus are of 3 varieties, and the 3 kinds take different trajectories. By filtering out all but one of the varieties, we can make a beam whose future behavior is the same kind, and the same kind of apparatus is determined and predictable. So it's kind of like when you left or right turn, it's that there's a moment as about it, and then everything carries and goes on in that way. besides the sum of histories that arrive at that point, and the sum of the potentials in the action applied by intelligence according to usually an action on the free image of all information around it, makes left right and straightening out, turning and turning. Stern-Gerlach relates to this as an atomic model of the particles in terms of the waves, whereas in the classical scale, this is still one system of inertial things that overall is an inertial system in a frame, in a space. And overall, it's that ad infinitum is an inertial system in a frame, in a space, vis-a-vis that independent rotating frames are independent in their space. By filtering out all but one of the varieties, or filtering or as kind of compounding them together, we can make a beam whose future behavior is in the same kind of apparatus as determined and predictable. We call this a filtered beam or polarized beam, or a beam in which the atoms are known to be in a definite state. So it introduces polarization, and whether that's so for polarization or if it's an aspect that just results it's not different than polarized, is kind of a thing, because oftentimes polarized will be diminish the overall energy, but I guess we just call this polarized as well. And with regards to then the idea of before about the momentum polarization or phase momentum is that polarization and phase are kind of related. So I was thinking kind of mostly about phase with regards to the polarizing, and with regards to the wave profile is usually associated with effects in the optics and the gratings and the diffraction in reflection and refraction. For the rest of our discussion, it will be more convenient if we consider a somewhat modified apparatus of the Stern-Gerlach type. The apparatus looks more complicated at first, but will make all the arguments simpler. That's not good. Anyway, since they are only thought experiments, it doesn't cost anything to complicate the equipment. Incidentally, no one has ever done all the experiments we will describe in just this way, but we know what would happen from the laws of quantum mechanics, which are, of course, based on similar experiments. I can't really... That's not scientific, of course. These other experiments are harder to understand at the beginning, so we want to describe some idealized but possible experiments. Now, Feynman, I would be kind of angry at him for suggesting that I suspend my science in the interests of keeping things simple or unsurprising. Well, at the same time, it's to be appreciated. His statement is like, we read this interpretation in our theory. He's kind of stretched the envelope to say it's like there's an envelope is outside the box here. Going on. So he shows a drawing they would like to see, and what he does is he sends a ray between blocks and wedges with alternating north-south poles, and I imagine that he might tell us that what he'll get out of it is a no result. Let's see. Shows a drawing of the modified Stern-Gerlach apparatus we'd like to use. It consists of a sequence of 3 high-gradient magnets. The first one on the left is just the usual Stern-Gerlach magnet. It splits the incoming beam of spin 1 particles in 3 separate beams. Second magnet has the same cross-section as the first, but is twice as long, and the polarity of its magnetic field is opposite the field in magnet 1. Second magnet pushes in the opposite direction on the atomic magnets and bends or passes back toward the e-axis, as shown in the trajectory shown in the lower part of the figure. Third magnet is just like the first and brings 3 beams back together again. So they leaves the exit hole along the axis. Finally, we would like to imagine that in front of the hole at A, there's some mechanism which can get the atoms started from rest, and after exit hole B, there's an accelerating mechanism that brings the atoms back to rest at B. That is not essential, but it will mean that in our analysis, we won't have to worry about including any effects of the motion as the atoms come out. We can concentrate on those matters having only to do with all the spin. The whole purpose of this improved apparatus is just bring all the particles to the same place and with zero speed. Now, if we want to do an experiment like the one in 5.2, we can first make a filtered beam. Now, if we put the polarized atoms through a second identical apparatus, all the atoms will take the upper path. Now he's describing having two Stern-Gerlach apparatuses in a row. And what he doesn't make clear is why that first one will be the same. So the first one, he's just got it goes one way. So in the second one, he's described his modified apparatus that bends stuff out and then keeps things going. And so he's put two of those in a row. The improved Stern-Gerlach apparatus is a filter. Suppose we call the first apparatus by the name S. We are going to consider all sorts of combinations. We'll say that the atoms which take the top path in S are in this plus state with respect to S. The ones which take the middle path are in the zero state. The ones which take the lowest path are in the minus state. And in the more usual language, we would say that the Z component of the angular momentum was plus 1 H0 and minus 1 H. And measuring things here in terms of Planck lengths. We are not using that language now. Now in figure 5.4, the second apparatus is oriented just like the first, so the filtered atoms will all go on the upper path twice. Or if we had blocked off the upper and lower path in the first apparatus and let only the zero state slide through, all the filtered atoms would go through the middle path of the second apparatus. If we had blocked off all but the lowest beam in the first, there would be only a low beam in the second. We can say that in each case, our first apparatus would produce a filtered beam in a pure state with respect to S plus 0 or minus, and we can test which state is present by putting the atoms through a second identical apparatus. So this is that when you're turning, you can kind of feel acceleration, and when you let out, it's done. You know, that's how you can test that it's complete, the action. What results straight, turning straight. It's just kind of described here in terms of the Stern-Gerlach apparatus. The idea of the forces in effect with regards to these notions of left, straight, and right, and plus 0 and minus, say. We can make our second apparatus that transmits only atoms of a particular state and then test the state of the incoming beam just by seeing whether anything comes out the far end. To make this kind of discussion easier, we're going to invent a shorthand symbol, and it's plus 0 minus. So the symbol stands for the apparatus, and we block one of their beams at the side. We'll mark that with bar next to it. It shows that it's blocked. Put the symbols together, you expect everything to come out, and then he'll show that just whatever his arithmetic signs that add up and keep together and come out. What don't will have nothing out of it. So you expect there to be a null result. Then we let bracket B given A ket, bracket B A ket, be the amplitude that an atom which is in state A will get through an apparatus into the B state. We can, and this is just whether it gets out at all. We can say that B given A is the amplitude for an atom in the state A to get in the state B, because bracket just means conditional probability. Is given ket. The experiment gives us that plus S given plus S equals 1, minus S given plus S equals 0, plus S given minus S equals 0, and minus S given minus S equals 1. And so he's relating that to how those are like so, and saying, look, this is just like our conditional problem attitudes. And it's like, actually, that's just left and right in your system. It says, now comes the big question. What happens if the second apparatus is tipped to a different angle so this field axis is no longer parallel to the first? It could be not only tipped, but also pointed in a different direction. For instance, it would take the beam off at 90 degrees with respect to the original direction. I imagine that it would go any which way, because it's a super classical wave on the skin effect on the outside. So how it winds around that will kind of depend on the phase and the orientation and how the wave would go around with regards to the waveguide. So here we're just talking about reflections with regards to, back in the discussion of waves, waveguide. Take it easy first. Let's first think about an arrangement, which is second Stern-Gerlach experiment is tilted by an angle alpha about the y-axis. So he shows one that lines up with 1, and then he lines up with nothing. What comes out of the far end in these cases when it's set to alpha? The answer is this. If the atoms are in a different state with respect to S, they are not in the same state with respect to T. A plus S state is not also a plus T state. There is, however, a certain amplitude to find the atom in a plus T state, or a 0T state, or a minus T state. So he's like, your bets are off, which is fine. In other words, as careful as we've been to make sure that we have the atoms in definite condition, the fact of the matter is if it goes through an apparatus which is tilted at a different angle, it has, so to speak, to reorient itself, which it does, don't forget, he says, by luck, or probability, or the law of large numbers reflected by a very, very large number, what results in the classical scale, how it all comes together at one instant in a moment. You can put only one particle through at a time, and this is according to electron physics. What is the probability that it gets through? It'll vary. These odds can be calculated by the absolute squares of complex amplitudes. But what we want is some mathematical method or quantum mechanical description for these amplitudes. What we need to know are various quantities like minus t given plus s, which should be 0, I think. But that's for alpha being 0. But at 90 degrees, you might figure that at 90 degrees, or where the angle is the same as this incident angle, as we were talking about the breaking radiation, and where the angle would line up because the angle is a function of the energy involved. So if you can point it at that, then you might expect that it would have a perfect reflection off that, with regards to making orthogonality and affecting state change of one or the other, or being half of that and affecting state change of one or the other in the waveguide, as it were. Thus it makes 9 amplitudes. Just as F equals ma tells us how to calculate what happens to a classical particle in any circumstance, if you know all the different forces on it and all the different instances and add them all up to all the different points of application, integrate the entire sum of histories, given the entire sum of potentials, F equals ma, tells us how to calculate what happens. The laws of quantum mechanics permit us to determine the amplitude that a particle will get through a particular apparatus. And he says the central problem then is how to be able to calculate for any given tilt angle A, or in fact for any orientation whatever, the 9 amplitudes. You can already figure out some relations among these amplitudes. First, according to our definitions, the absolute square is the probability that an atom in a plus S state will enter a plus T state. Well, he's just writing out the expressions that do result these things, not what they are yet. We'll find it more convenient to write such squares in the equivalent form of plus t given plus s times plus t given plus s star, or the adjoint of that. I forget my Hermitian and my Hamiltonians and stuff like that, and Brown Cat a little bit. But what it means is when that's squared, it kind of results as that it's the real part and this and that. The same notation, the number for 0t given s and 0t given s is the probability of the particle that this and that. And that minus s results, it's a negation formula, and it just says one way or the other. But the way our apparatuses are made, every atom which enters the T apparatus must be found in some one of the 3 states of the T apparatus. There's nowhere else for a given kind of atom to go. So they must add up to 1. So it says, but if we can find if we can find two out of these three, then the third would be unknown. These are equations and variables in unknowns, which Feynman here has written. But they are all we can easily get, so we'll go on to some other general questions. Well, that's nice. I mean, he's just kind of laid it out this way. And he says, he goes into this other ideas. So now the ideas are, for Stern-Gerlach in series, we want to know how these come through. And we got the angle A. And then we have added a third one in this series that has the same configuration as the first one, at least. So he calls them ST and S prime. And then he shows by the chaining up the brackets that S given 0t times 0t given 0s is the probability. Writing out squares, writing that out as the sum of the squares, their magnitudes, or rather, according to triangle law, or the inner product, the direct product of the brackets. There's square being the product of their magnitudes, their squares. And then writing in a ratio, which gets in the whole definition of complex numbers, as according to 1 over I, we would of course find the same result. Compare the probabilities. So he's given expressions for these, and they've got unknowns. We would find a ratio such as the magnitude of r given 0t squared, or the magnitude of plus r given 0t quantity squared, was independent of which beam was passed by the first filter S. These results illustrate one of the basic principles of quantum mechanics. Any atomic system can be separated by a filtering process into a certain set of what we call base states, and the future behavior of the atoms in any single given base state depends only on the nature of the base state, is independent of any previous history. So what he's saying is that in this case, the quantum mechanics in the Stern-Gerlach apparatus is a continuous process. So that said, well, that's kind of the talk for today. It's got split up a little bit with regards to the idea of meters per second or seconds per meter being a dimensionless quantity. With regards to the dimensional resonator and the dimensionless resonator, having that, then it results that it's for mathematics to come up with these formulas that make it so that the models and the application of these tendencies and propensities, the tendency for an object to stay in motion or at rest, and the propensity for something to change it, combined with the formally non-zero attenuation and dissipation, that an object tends to go to rest, and what comes up must come down, and anything that's in like a constant field, like, for example, where it's lived its whole life, vis-a-vis an arbitrary deep field, where all fields are far fields, and what that means, and then getting into the constants and what that means for classical mechanics and classical dynamics, with all that their usual terms, and that they're real in the limit, in the pointwise, and the linear, or as arbitrarily contrived for model applications. That then as well, there is definitely kind of a perceived idea. Here's just another idea that this dimensional resonator or dimensionless resonator idea is towards getting that the dimensional analysis better supports the usual theories and usual laws of physics, and then also that it has what it needs as relations to quantities and operators on the quantities with regards to their dimensions in terms of classical mechanics and the application of forces in 3 dimensions in time is all it really boils down to is that for these different fields with regards to their interactions in effect, kinetics and kinematics here, that's sort of the talk for today if split into 2 parts, and that I shall so hope it finds you good and well today, and spring will soon be here. Happy Easter, as it were. And warm regards. Moment in motion. Geometry is motion.